In this video, we're going to talk about how to calculate the pH of a weak acid solution, as well as the pH of a weak base solution. We're also going to talk about percent ionization and some other problems associated with weak acids and bases. But let's review some basics. Now, if you recall, when a strong acid like hydrochloric acid reacts with water, because it's a strong acid, it will dissociate completely. So we could use a single arrow to represent this reaction. So if the initial concentration of HCl, let's say it's 0.05, as it dissociates completely, the hydronium ion concentration will be the same. So you can just calculate the pH of the solution using this formula. The pH is equal to negative log of H3O plus. And if you need to calculate the pOH, let's say of a strong base solution, you could use this, negative log OH minus. And remember, the pH plus the pOH adds up to 14 at 25 degrees Celsius. So if you know the pOH is simply 14 minus the pOH. Now, when dealing with a weak acid solution, the situation is different. A weak acid doesn't dissociate completely. So we're going to use a double arrow to indicate a situation of equilibrium. So this reaction is reversible. So when dealing with a weak acid or a weak base, or let's say a weak acid, you need to use something called Ka, the acid dissociation constant. It's an equilibrium constant, and it's equal to the concentration of the products divided by the concentration of the reactants. Water is a liquid, so remember, liquids and solids are not included in the equilibrium expression. Everything else is in the aqueous phase. It's dissolved in water, so you do include them in the equilibrium expression. Now, once you calculate H3O plus using ice table, so you can calculate the pH using the equation that we just considered. Now, when dealing with bases, in this case, NH3 is a weak base, you need to use the base dissociation constant, which is Kb. Kb, like Ka, is equal to the concentration of the products divided by the concentration of the reactant. Now, using ice tables, you want to calculate the concentration of hydroxide, because once you have that, you can calculate the pOH using this formula. And then once you have the pOH, you could find the pH. Now, sometimes you may need to calculate Kb from Ka, or vice versa. So remember, Ka times Kb is equal to Kw, which is 1 times 10 to the minus 14. And this is temperature dependent. So this equation holds true at 25 degrees Celsius. Now, sometimes you may need to calculate the H3O plus concentration from pH, and this formula will help you to do that. It's equal to 10 raised to the negative pH. Now, if you need to calculate the hydroxide ion concentration, it's 10 raised to the negative pOH. And also, the hydronium ion concentration times the hydroxide ion concentration at 25 degrees Celsius, this is equal to Kw, the auto ionization constant for water, and that's 1 times 10 to the negative 14. So those are some other formulas that you want to be familiar with. Now let's talk about acid strength. I've covered this in some other videos, but nevertheless, it's a good concept to review. Acid strength increases with increasing Ka values. So if you have two acids with two different Ka values, the stronger acid is the one with the higher Ka value. Now, acid strength is inversely related to pKa. So the stronger acid is going to have the lower pKa value. pKa is equal to negative log of Ka. And pKb is equal to negative log Kb. So you want to add these formulas to your notes if you haven't done so already. Now, the pKa plus the pKb, these two, they add up to 14 at 25 degrees Celsius. Now, the next thing we need to talk about is how to calculate percent dissociation, also referred to as percent ionization. Percent ionization is equal to X divided by the acid concentration, that is the original acid concentration that was dissolved in the solution, times 100%. X represents the amount of acid that is dissociated. And when dealing with acids, for the most part, X is usually the H3O plus concentration. So you can find it from doing an ice table, or if you know the pH, you can find it that way as well. When dealing with weak bases, X is usually the hydroxide concentration. So those are the formulas that we're going to be using throughout this video to calculate different things. So let's go ahead and work on some practice problems. Let's put these equations to good use. So what is the pH of a 0.75 molar acetic acid solution? And we're given the Ka. So first, let's write the dissociation reaction of acetic acid when it's combined with water. So because it's a weak acid, it's going to be a reversible reaction. So we need to put two arrows. Whenever you add a weak acid in water, it's going to generate the hydronium ion, H3O+, and also the conjugate base, which in this case is acetate. So what we're going to do is we're going to make an ice table. The initial amount of acetic acid is 0.75, and this is going to be units of molarity. And for the products, we're going to start with 0. Now the reaction has no choice but to shift to the right. It can't shift to the left. So the products will increase by X, and the reactant will decrease by X. We don't have to worry about water because water is a pure liquid. Everything else is in the aqueous phase. So as you recall, you can't have any liquids or solids in the equilibrium expression when you're dealing with Ka or Kb or any type of K. So if we add the first two rows, it's going to be X and 0.75 minus X. Now, in order to calculate the pH of the solution, we need to calculate the concentration of H3O+, which we could see that it's equal to X. So we got to find the value of X. So we can write the expression for Ka, the acid dissociation constant. It's equal to the concentration of the products, which can be found on the right side. That's H3O+ and the acetate ion, divided by the reactants. And we can't use water since it's a liquid. Now Ka is equal to 1.8 times 10 to the minus 5. H3O+ and acetate, they're both equal to X. Acetic acid, at equilibrium, it's 0.75 minus X. Now because 10 to the minus 5 is pretty small, we could ignore this X. So therefore we could say that Ka, or this number, is equal to X squared divided by 0.75. Now let's get rid of a few things. We really don't need this anymore. But keep in mind that H3O+ is equal to X. Now, in order to find the value of X, we need to cross multiply. So 1 times X squared is X squared. And 1.8 times 10 to the minus 5 multiplied by 0.75, that's equal to 1.35 times 10 to the minus 5. Now let's take the square root of both sides. So the square root of that number is going to be 3.674 times 10 to the minus 3. That's the concentration of H3O+. Now that we have the concentration of H3O+, we can calculate the pH of the solution. The pH is equal to negative log of the hydronium ion concentration. So it's a negative log of 3.674 times 10 to the minus 3. So you should get about 2.43. So that's the answer for this problem. That's the pH of the solution. So if you want to quickly get the answer, whenever you have a weak acid, and if you're given the concentration and the Ka value, and you want to find the pH, let's simply review the steps. First, use this equation. It's going to be Ka, which is equal to x squared, divided by the acid concentration, minus x. Now, if Ka is very small, if it's like 10 to negative 5 or less, typically you can ignore this x value. If Ka is not very small, then you may have to use the quadratic formula. So once you get the equation in this form, ax squared plus bx plus c, if you can't ignore this x, here's the quadratic formula that you need. It's negative b plus or minus the square root of b squared minus 4ac divided by 2a. So keep this in mind. If you're going to use the quadratic formula, you need to rearrange the equation until it's in this form. So on one side of the equation, you have to have a 0. Now, when you're dealing with when you're dealing with Ka, x is equal to H3O+. So once you find the value of x, you can calculate the pH using this equation. Number 2. What is the pH of a 0.25 molar ammonia solution? And we're given the Kb, the base dissociation constant. So, since we have Kb, basically we have a weak base in the solution. And a weak base will generate hydronium ions. So we need to use Kb to find x, which x is going to represent the hydroxide ion concentration. And once we have that, we could find the pOH of the solution and then the pH. So first, let's write a reaction. When you put a weak base with water, it's going to be a reversible reaction, and you're going to get the conjugate acid, in this case NH4+, and hydroxide. So let's make an ice table just as we did before. The initial concentration for ammonia is 0.25. The products will begin at 0, and the reaction will initially shift towards the right. So add in the first two rows, we're going to have 0.25 minus x and x and x. So Kb, like any other equilibrium constant K, it's going to be the concentration of the products divided by the reactants. And don't include water. Now Kb, we know it's 1.8 times 10 to the minus 5. NH4 plus and OH minus, they're both equal to x. X times x is x squared. And NH3 is 0.25 minus x. But since Kb is small, we could ignore the x that's next to the 0.25. So we're going to get this equation. So let's cross multiply. So we're going to have x squared is equal to 0.25 times 1.8 times 10 to the minus 5. And that's 4.5 times 10 to the minus 6. Now let's take the square root of both sides. The square root of 4.5 times 10 to the minus 6, that's 2.12 times 10 raised to the minus 3. Now that we have the value of x, we have the concentration of hydroxide, which means we could find the pOH of the solution. So the pOH is negative log of the hydroxide concentration, or of 2.12 times 10 to the minus 3. So this is equal to 2.67. And whenever you have the pOH of a solution, you can easily find the pH. It's going to be 14 minus the pOH. So the pH is about 11.33. And so that's the answer for this problem. So this is what you need to do if you need to find the pH of a solution that contains a weak base. Number 3. What is the pH of a 0.4 molar ammonium chloride solution? So in this problem, we want to find the pH of a salt solution. Ammonium chloride is an ionic compound, and we're given the Kb of an NH3. So what should we do in this problem? We need to realize that NH4 plus is a weak acid, because NH3, the conjugate base, is a weak base. So let's write the reaction when it's added to water. So because it's a weak acid, it's going to donate a proton to water. And so we're going to get the H3O plus ion and also NH3. So NH4 plus is the acid, it's the proton donor. Water is the base, is the proton acceptor. H3O plus is the conjugate acid. NH3 is the conjugate base. Now let's make an ice table. So initially, this is going to be 0.4, and as usual, this is 0, 0. The reaction is going to shift to the right, increase in the products by X, decrease in the reactants by X as well. Now, in this problem, should we use Ka or Kb? What do we have in the solution? Do we have a weak acid or a weak base? We don't have NH3 in the solution initially. We have NH4 plus, and that's a weak acid, which means we need to use Ka. Ka is always associated with H3O plus. If you have something that produces hydroxide ions, that's going to be associated with Kb, which is a base, or which is 4 bases. So we have a weak acid in a solution, we need to use Ka, but we're given Kb. So how can we find Ka from Kb? Ka times Kb is equal to Kw, which is the autoionization constant of water, and that's equal to 1 times 10 to the negative 14. So therefore Ka is basically equal to that number divided by Kb. And we have Kb, it's 1.8 times 10 to the negative 5. So let's go ahead and divide these two numbers. So this is about 5.56 times 10 to the negative 10. So now that we have Ka, we can write the equilibrium expression, which is going to be products over reactants. So we know it's going to be x squared divided by 0.4 minus x. Now Ka is very, very small. So therefore, we can neglect this x value. It's going to be insignificant. Now let's cross multiply. So we're going to have x squared, which is equal to 0.4 times 5.56 times 10 to the minus 10. As usual, we're going to take the square root of both sides and calculate the value of x. So x is 1.49 times 10 to the minus 5. Now, because we're dealing with Ka, X represents the H3O plus concentration, which means we can now find pH directly. So the pH is going to be negative log of the hydronium ion concentration, which is equal to X. So therefore the pH is about 4.83. That's the answer. Number 4. What is the pH of a 1.5 molar sodium fluoride solution? So we're given the Ka of hydrofluoric acid. Let's go ahead and find the pH. So we don't have to worry about sodium. It's a spectator ion, so let's ignore it. By the way, feel free to pause this video and work on this problem yourself. See if you can get the answer. So fluoride is the ion of interest because it's associated with HF. If HF is a weak acid, fluoride is basic enough to change the pH of the solution. So fluoride is a weak base. It's going to react with water, and it does so reversibly, generating the conjugate acid HF. And because fluoride is a weak base, it's going to generate a small amount of hydroxide ions, thus changing the pH of the solution. So we're going to make our ice table as usual, and the initial amount of fluoride is 1.5. The products are 0, and they're going to increase by X. Fluoride will decrease by X. And as you can see, the ice table for the most part is pretty much the same. Now, we need to find Kb because fluoride is a weak base. We have sodium fluoride in the solution, not HF. We're going to have a small amount of HF, but for the most part, we have a large amount of sodium fluoride. So we need to use Kb. Kb is going to equal the products divided by the reactant. So let's go ahead and find Kb. Kb is going to be equal to Kw, which is 1 times 10 to the negative 14, divided by Ka, which is this number. So Kb is 1.39 times 10 to the minus 11. HF and hydroxide, they're both equal to X, so X times X is X squared. And F minus is going to be 1.5 minus X, but we could ignore that X since Kb is very small. Let's cross multiply. So this is going to be X squared, which is equal to, let's get rid of this X. 1.39 times 10 to the minus 11 times 1.5, and that's 2.085 times 10 to the minus 11. Now let's take the square root of both sides. So X is equal to 4.566 times 10 to the negative 6. Now keep in mind that X is equal to the hydroxide concentration. So we could find the pOH, and then we could find the pH of the solution. So the pOH is equal to negative log of the hydroxide concentration, which is this number. So notice that you see a 6 here. The pH, the pOH is going to be somewhere between 5 and 6. So it's actually 5.34. Now that we have the pOH, we can calculate the pH, which is 14 minus the pOH. And it's going to be about 8.66. So that's the answer for this problem. Now you know how to calculate the pH of the solution if you're given a basic salt solution. Now let's focus on percent ionization problems. I'm actually mixing in some old videos that I had in the past. with this video. So what is the formula in order to find the percent ionization? It's equal to X divided by the acid concentration. Now, if you're dealing with a weak acid, X represents the amount of H plus that is in equilibrium in a solution. And let's not forget to multiply this by 100%. Now, when you're dealing with bases, X represents the amount of hydroxide. And instead of HA, it's going to be the concentration of the base. That is the initial concentration. So now, let's go ahead and write a reaction. So once a weak acid is in a solution, let's say when it's dissolved in water, it's going to ionize. And because it's weak, the reaction is going to be reversible. So we need to put two arrows. Acids will always generate H3O+, the hydronium ion, and we're going to get the conjugate base, fluoride. So now let's make an ice table. The initial amount of hydrofluoric acid is 0.75, and initially we don't have any hydronium ions or fluoride ions. So therefore the reaction has no choice but to shift to the right, increasing the products by X, decreasing the reactants by X. So if we add the first two rows, this is what we're going to get. Now, Ka, the acid dissociation constant, like any equilibrium constant, is equal to the ratio of the products over the reactants. So Ka is equal to 7.2 times 10 to the minus 4. H3O plus and F minus, they're both equal to X. X times X is X squared. And HF is 0.75 minus X. So basically, we're using the values at equilibrium when dealing with K. Now, because Ka is fairly small, we can ignore this X. X is going to be relatively small compared to 0.75. So what we can do at this point is cross multiply. 1 times X squared is X squared, and 0.75 times Ka, that's equal to 5.4 times 10 to the minus 4. Now let's take the square root of both sides. So X is equal to 0.0232. So 0.75 minus 0.0232, that's about 0.7268. It doesn't change that much. It changes a little, but we're going to go with this estimation. So now that we have the value of X, we can calculate the percent dissociation. Now keep in mind, this is not the exact answer, but it's an estimation of the answer. To get the exact answer, you can use the quadratic formula, but we're just going to go with the estimation. So the percent ionization is going to be equal to X, which is 0.0232, divided by the initial concentration of HF, which is 0.75. So it's about 3.1%.